So the next thing that we're going to be doing now, we're going to be giving an overview of the Lavaan package. So this is the package that is used for performing SEM analysis in R. So I'm going to be talking about how we can get started with Lavaan and how can we use it to perform structural equational modeling in R. So first of all, we need to know what Lavaan is. Lavaan is actually an acronym that stands for Latent Variable Analysis. It's an R package for structural equation modeling, and it allows you to be able to plot. It has also other packages which allows you to be able to plot your hypothesized diagrams and also show the relationship between the variables you're having in your model. So how do you get started with Lavaan? First of all, you install the package using install.packages function. You install packages Lavaan, then you also load the package using the library function. You load the package into R. So if you want to create a model object, this is where you define the relationships you have in your variable. So this is just a simple model object you are looking at. In this particular model object now, you see we have a single latent variable and we have two observed variables. So how do we know that they're actually latent variables? Because of this particular sign, an equals to sign and a tilde sign. So you can see it here. So it means that the latent variable y is observed from these two observed variables, x1 and x2. So this is how you can define a simple relationship between variables inside your model. So model object specifies relationship between observed and latent variables, and also the sign I talked of now specify observed variables to latent variable relationship. And also you can see this particular sign now, which is called where I said is the tilde sign earlier on. It allows you to specify. If you give only this sign, I know most of you are familiar with this. It specifies regression between what a dependent variable and an independent variable. So imagine if it was only this particular tilde sign now without any equals to, they can now say that what x1 and x2 are predicting what our outcome variable y. But because we have an equals to and a tilde sign, we now say x1 and x2 are observed variables which are being caused by what the latent variable y. So this is how you can create your model object using these signs. We also have another sign where we have a double tilde. This specifies covariance or covariance between two variables. So we have two variables that are related to each other or having covariance between each other, then we use this particular sign to specify a model inside the model object. So this is just a simple model object where x1 and x2 are the observed variables, while y is the latent variable. So the next thing now, I want to fit the new model. I've already defined your model object, which is where you define your relationship between variables. Now is to fit the model. So I'm going to create an object called fit. This is where I'm going to be storing our model. Then use the same function where you first of all give your model object, then you now give in your data. In this example now, the data I'm using now is my data. So that's what I'm giving in this particular same function. So the same function only takes two composite variables, that is your model object and also your data. They also have extracting results from the model now. So I've already fitted that particular model now inside fit object. Now I want to extract the result from the model. You're going to give in the name of your model, fit, and also you can give the option of standardize equals to true or standardize equals to false. So most of the time you can standardize it when you are having variables that are not on the same scale. So this is where you usually give standardized equals to true. If you have some observed variables that are not on the same scale, you give standardized equals to true. You're having outliers in your data, you give standardized is equals to true. So this is how you can just extract the result from the model. So it's just three basic steps. First of all, you specify your model object, you fit your model, and you also extract your results from your model. So the next thing now we're going to be going to now is the model interpretation. So I've already fitted the model now, I've already gotten our result. How do you now interpret this particular model? So what we're going to be doing now, first of all, we're going to be talking about interpreting parameter estimate and standard errors. So we have what we call parameter estimate and standard errors. So parameter estimate are just values of coefficients calculated for each predictor variable in the model. So this shows us the magnitude of that particular predictor variable. You have already gotten values for your latent variable, and you are predicting your latent variable now on another maybe latent variable. Because most of the times you are using this SEM because you want to have something for the latent variable from observed variables. But maybe in your analysis, you want to predict two latent variables on another latent variable. So now you have already gotten the coefficients of these latent variables. So for you to know what is the magnitude and how do they affect that predictor, how did they affect that particular outcome variable. So this parameter estimate allows you to give that interpretation. I also have standard errors, which are measure of uncertainty in the estimation of coefficients. So the higher a standard error when you have in a coefficient, the more uncertain that particular coefficient is, which means that the lower standard error, the better the coefficient is, and the more it explains your outcome variable. So standard error allows you to measure uncertainty in the estimation of these coefficients. And we also have the fit indices and goodness of fit test. So these are metrics which allows you to be able to test how good your model fit is, because you want to know the kind of model you have, the analysis just conducted now, how good is this particular model. Is this something that is explaining your data well, or is something that's only explaining few factors or few effects inside your data. So the fit indices and good fit of measures the good fit or goodness of fit of the model. And these fit indices include chi-square. We have a chi-square. You can also use chi-square to check if your SEM analysis is if your SEM model is a good fit. We have the root mean square error of approximation, RMSEA. We also have the comparative fit index, CFI, and also have the Tucker-Lewis index, TLI. We have the standardized root mean square residual, SRMR. So these are metrics which you can use to see how good your model fit is. And these metrics have bench values. For that of the chi-square, a non-significant chi-square value indicates a good fit. So that means if you have a value that is higher than 0.05, let's say you are using a 95% confidence interval, and you have a value higher than 0.05, this indicates that your model is a good fit. So one disadvantage of the chi-square, why is most of the time it's not a reliable fit index, is because it's actually susceptible to a large sample size. So even if your model is good or bad, if your sample size is large, there's likely to return a non-significant chi-square value telling you that my model is a good fit, which might not actually be true. So that is why we also have other ones like the RMSEA now, root mean square error of approximation. This one's a value of 0.05 in the is considered a good fit, or less is considered a good fit. So anytime you have a value of RMSEA less than 0.05, you are knowing that yes, you are having a good model fit. While a value between 0.05 and 0.08 indicates a reasonable fit, that is also acceptable range. But any value above 0.1 is considered a poor fit. Then we have the CFI, comparative fit index. This is a value of 0.9 or above indicates a good fit, while anything above 0.95 indicates an excellent fit. So which means in a CFI, if you're having a value of 0.1, 0.2, then you're having a very poor model fit. Then we have the CSI, Tucker-Lewis index. This is a value of 0.9, just like the CFI, also indicates a good fit. A value of 0.95 indicates an excellent fit. So any value that is also falls between less than this range. Sometimes in some literatures, any value of 0.8, 0.85 is also acceptable. But every time we're talking of value of 0.2, 0.3, then this is an indication of a poor model fit. Then we have standardized root mean residual, SRMR, which a value of 0.08 is considered or less is considered a good fit. This is something similar to so in an SRMR, a value of 0.08 is or less is considered a good fit, while a value between 0.08 and 0.10 indicates a reasonable fit, while values above 0.1 are considered a poor fit. So this is also something similar to what we have been saying, except that for that of the RMSEA it was 0.05. So sometimes it also depends on your use case or the kind of data you are dealing with. For example, more sensitive data like health data requires more penalization or more penalty,